Hi friends, in this video we are going to discuss about the concept of mesh analysis. So this mesh analysis concept is very important concept in the electrical networks, and here actually the main purpose, what is the main purpose of this mesh analysis concept and why we are going for this mesh analysis concept in the electrical networks means, for example, just see this particular network here. So whatever the network here visible, so just observe this particular network. So here this is a network, we are having one voltage source is there, and we have R1, R2, R3 resistances are connected in the network. And here the question is, just in this question, just see, find the currents flowing in the individual loops. Okay, find the currents flowing in the individual loops for the following network by using mesh analysis concept. Okay, so whatever the topics we discussed in the previous, so in that particular problems, what we calculated, we are calculated the current flowing in the individual branches or current flowing through particular resistances. So to find that particular resistances, we are going to use a current division rule. So with the help of current division rule, we calculated the currents flowing in the individual branches. Okay, so to find the currents flowing in individual branches of resistances, we can directly apply Kirchhoff's current division rule directly. But in case of the question is what? Find the value of currents flowing in the loops. Okay, loop. What is the meaning of loop actually? The meaning of loop means mesh, or we can also call as, the meaning of mesh means loop. Any closed path we are calling as loop, are also called as mesh. Okay, the meaning of loop or mesh, both are same. Here the question is, find the current flowing in the individual loops. Okay, so here the meaning of loop is mesh. So that is the reason why the concept of mesh analysis is always used in the electrical networks to find the currents flowing in the loops. Okay, so I am writing here. So the main concept of this particular mesh analysis is what? So first thing is finding the currents flowing in the loops, or individual loops. Okay, so for example, see here, in this network we have two loops. Okay, this is completely closed path and this one is also completely closed path. It means we have two loops, means we are going to get two currents. Okay, so that is the reason why in loop number 1 the current is I1, in loop number 2 the current is I2. Now we need to find these two currents which are flowing in the loops. Okay, now see here, come to the concept of mesh analysis. First point is finding the current flowing in the loops. But how we are going to find these particular currents which are flowing in the loops means by applying Kirchhoff's voltage law, that is what? KVL. So by applying KVL in the loops. Okay, so by applying KVL in the loops, then by applying KVL in the loops you will get expressions. So by applying KVL in the loops means you are getting expression, means whatever the expression we are getting from the network, those expressions is equal to the number of loops in the network. It means in this network we have two loops, that's why you are going to get two expressions. Okay, so two expression, by applying KVL in the loops you will get the expressions, and these particular expressions is equal to the number of loops present in the given network. Okay, now after getting expression, what is the next step? Just simplify. So just simplify all these equations, then you will get currents which are flowing in the you are going in the what? Loops. Clear? So this is a concept we need to follow when we are going to apply mesh analysis in electrical networks. Okay, now see here, first point is finding the currents flowing in the loops. But how we are going to finding these currents? By applying Kirchhoff's voltage law, that is KVL in the loops. Now applying KVL in the loops, then you will get expressions, and the number of expressions must be is equal to number of loops present in the given network. If suppose we are having 10 loops, then you will get 10 expressions. If suppose we are having 2 loops, then you will get 2 expressions. After getting the expression, just to simplify all these expressions or equations, then you will get the currents flowing in the loops. Clear? So this is the procedure we need to follow to get the unknown currents or currents flowing in the loops. Clear? Now see, we are going to solve one problem, and whatever the problem we are taken here, same we need to consider this problem and get the solution for this particular problem by using this procedure. Clear? Now see here. Now see, yes, so again I am drawing the same network here. So this one is a voltage source, and we have one resistor R1, R2 and R3. These are the resistances connected here, and here the value of this particular voltage source is 10 volts. The value of R1 is equal to 5 ohms. The value of R2 is equal to 10 ohms, and the value of R3 is equal to 20 ohms. Clear? So what is our target actually? Find the current flowing in loop 1 and loop 2. Okay, now see here the most important points I am going to discuss now. Now how we can say that the direction of current is always like this? Just see here, in this problem the current direction is, or the flow of current is always in the clockwise direction. I am taking in the loop number 1 and loop number 2. How we taken this particular direction of currents which are flowing in the loop means the direction of currents flowing in the loop always depending upon the voltage source. Okay, so voltage source, how the voltage source is connected in the network. So depending upon the positive terminal of a voltage source, so the current will flows like that. For example, what I am telling you, in this particular network the voltage source is connected here. It means this is the positive terminal. It means the current will always start from the positive terminal 2 and end at negative terminal. That is the reason why the current flowing in the loops, current flowing in the loop number 1 and loop number 2 follows the direction based on the positive sign of this particular voltage source. Clear? So that is the reason in this problem we have taken the direction depending upon the positive terminal of a voltage source. And after that we are going to discuss so many problems based on the mesh analysis concept, and I am going to solve more number of problems because if you are going to get the, if you want to get the more knowledge how to solve the problems by using the mesh analysis concept, so if you are going to clear with all these problems, okay, so when we are going to do more and more problems, then you will get full clarity. Okay, so in this problem we are taking the direction of this particular current always depending upon this particular voltage source. Okay, in the next problem we will take another voltage source and current source, then how we are going to find the currents in the loops, that is a question. Okay, now see here, the currents flowing in this particular loop number 1 and loop number 2 is clockwise direction. Clear? Now here, after identifying the direction of current, what is the next step? Here the step number 1 I am taking here is apply. So apply KVL in loop 1 first. Okay, so what I am doing, first I am applying KVL in the loop number 1. Okay, now what I am doing here, when we are going to apply KVL in the loop, now first we need to identify which current is flowing through the R2 in the upward direction and which current is flowing in the flowing through the R2 in downward direction. Just see here, for example, what I am doing, this I1 is flowing in the clockwise, this I2 is also flowing in the clockwise direction, but when we are going to writing the KVL expression for the loop number 1, you have to observe this particular thing. Okay, so the as per the direction of I1, through this particular R2 the direction is downwards, clear. And again I2 is also clockwise, but through this particular R2 the direction of current is I2 is upwards. It means whenever we are going to get the voltage drop across this particular R2, we need to take or we need to consider both I1 and I2, clear. So what I am doing here, I am separately drawing the loop 1. Okay, so just see here, I am separately drawing the loop number 1 network because I need to apply KVL for only loop number 1, clear. So this one is R1 is equal to 5 ohm, V is equal to 10 volts, and this R2 is equal to 10 ohms, clear. Now see here, now see, so here R3 is connected, but we required only what? We required only this particular point, clear. Now see here, I1 is flowing like this only, but when this current is flowing like this, the direction of current is downwards through this particular R2, and here upwards through this particular R2, the current flowing in the loop, clear. Now by applying KVL in the loop number 1, so by applying KVL in loop number 1, how we are going to get the expression? We know that the definition of KVL is applied voltage must be is equal to sum of voltage drop across individual elements which are connected in the network. Okay, now just observe this particular network. So what is happening here, just see, when we are going to applying KVL in the loop number 1, applied voltage is what? Actually applied voltage is V is equal to sum of voltage drop, means R1 is connected to this particular loop 1. It means across this particular R1 we are going to get the voltage drop, that is VR1. And coming to here R2 is also connected for loop 1. Okay, so that is the reason we need to consider this particular R2 across the drop. Okay, the voltage drop across R2, clear. Now see here, by applying KVL in the loop, so applied voltage is equal to voltage drop across R1 plus voltage drop across R2. Okay, so V is equal to VR1 plus VR2. So by applying KVL, applied voltage V is equal to voltage drop across R1 and voltage drop across R2. But we know that V is equal to, what? V is equal to I into R. Okay, this is the formula we need to use, the voltage drop across individual elements. Now coming to use this formula to get the expression across this particular VR1 and VR2. Now see here, by using this particular expression, voltage drop across VR1 is equal, voltage drop across R1 is equal to current flowing through R1 into the value of R1, clear. So this is the VR1 expression. Now coming to VR2 is equal to current flowing through R2. Current flowing through R2 means here I1 is, not only I1 is flowing through R2, I2 is also flowing, because R2 is the mutual resistance connected between loop 1 and loop 2. So while we are writing the voltage drop across this particular R2, we need to consider the effect of I1 which is flowing in the loop 1 and I2 which is flowing in the loop 2. And even we are applying for the KVL in the loop 2 also, we need to consider this particular I1, I2, clear. So here VR2 is equal to, we are writing I into R, means two currents are flowing through R2. That's why I am writing I1 minus I2 into R2. Sir, why you are writing this particular I1 minus I2? Means I1 is the loop current 1 which is flowing through R2. I2 is the loop current 2 which is flowing through R2. But why we are taking this particular negative sign for I2 means when we are applying KVL for the loop number 1, the potential of I1 is always greater than I2. And when we are applying KVL for loop 2, the potential of I2 is always greater than I1. That is the reason why I am taking I1 minus I2. But why I am taking here negative sign means what? The direction of current is downwards. the direction of I2 direction of I1 current is downwards and direction of I2 is upwards. It means when we are going to get the voltage of across R2, the current, depending upon the current direction, we are writing like this. Clear? So I1 positive potential, I2 negative potential into the value of R2. Clear? So here we are writing VR2 is equal to I1 minus I2 into R2. Clear? So this is the voltage of across resistance 2. Now substitute this value and this value instead of VR1 and VR2. Clear? Now see here what I am doing here. Just simply I am substituting like this. So V is equal to VR1 means I1 into R1 plus VR2 means I1 minus I2 into R2. Clear? Now simplify here. What is the value of applied voltage in the loop 1? So applied voltage loop 1 is 10 is equal to I1 into R1 plus, again just multiply here, I1 into R2, that is I1 into R2 minus I2 into R2. Okay, so here this is I1, this is I1. Now take common I1 here. So 10 is equal to, so here by taking common I1 here you will get R1 plus R2 minus I2 into R2. Clear? So this is the expression we are getting from the loop number 1. Now what we need to do, we know the value of R1, we know the value of R2, we know the value of R2. Just substitute these values also in the expression. Clear? Now see here. So what we need to do, so 10 is equal to, so 10 is equal to, so I1 into what is the value of R1 here? R1 is 5 ohms, R2 is 10 ohms. Now here R1 is 5 ohms plus R2 is 10 ohms minus I2 into the value of R2 is again 10 ohms. Clear? Just see here in the network, in this particular network, R1 is 5 ohms, R2 is 10 ohms, R3 is 20 ohms. Now instead of R1 and R2, just we are substituting these values. Clear? Now see here. So 10 is equal to I1 into 5 plus 10 means what? 15 minus I2 into 10. So here 10 is equal to 15 I1 minus 10 I2. Clear? Now here what we are doing, I am writing this expression like this. So 15 I1 minus 10 I2 minus 10 is equal to 0. Now I am assuming this particular expression as equation number 1. Clear? Now this is the expression we are getting by applying KVL in loop number 1. Clear? Now the pending is what? Apply KVL in the loop number 2. Again you will get one expression. After getting the second expression from the loop number 2, just to simplify these two expressions, you will get the unknown values of currents. Those are what? Current flowing in the loops you will get. Clear? Now step number 2. Step number 2 is apply Kirchhoff's voltage law in loop 2. Okay, so apply Kirchhoff's voltage law in loop number 2. Now again what I am doing, this particular loop 2 diagram I am drawing separately here. Just see here. Okay, so here R1 is connected and here, so this one is R3 is equal to 20 ohm and this one R2. So here R2 is equal to 10 ohms and we don't require this R1 value because we are not going to consider this R1. Only we need to consider this loop 2 and how much amount of current is flowing through R2. That is enough. Okay, because we need to consider only the elements which are connected to only loop number 2. Clear? And what is the direction of this current in the loop 2? Again the direction of current I2 is in the clockwise only, but we know that in the loop 1 the current direction is like this. It means this I1 is exactly downwards to this particular downwards through this particular R2, and here the value of I2 is upwards through this particular R2. Now what we need to do, just see here, apply apply Kirchhoff's voltage law in loop 2. Now just observe the given network. The voltage source is connected for loop 1 only. Just see here, voltage source is connected for loop 1 only. For loop 2 there is no voltage source is connected, so that is a reason why we are not taking the voltage source in the loop number 2. Clear? Now see here, if we are not going, if suppose in the given network we have only voltage source for loop 1 means there is no voltage source for loop 2 means what is applied for voltage for this loop number 2? 0 only. Clear? So as per the KVL we are applying in the loop 2, the applied voltage is 0 is equal to the voltage drop across R3 we required and also R2 is also required. It means the voltage drop across R3 is VR3, okay, and the voltage drop across R2 is VR2. Clear? Now see here, VR3 and VR2 we need to get the expression from this particular network. Okay, now see here, VR3 is equal to current flowing through R3, that is what, I2 into that particular resistance R3. Clear? So this is the value of what, VR3. This is the voltage drop across R3. Now coming to the voltage drop across VR2, voltage drop across R2, that is what, VR2. Now current flowing through R2 into that particular resistance. Now see here, current flowing through R2 we are writing for what, R2. When we are writing the expression for loop number 2 means always the potential of loop 2 is current is always greater than the potential of this particular loop current I1 into that particular resistance R2. Okay, now initially when we write the expression for loop 1, I1 is greater than I2, that's why I am taken I1 minus I2. Now here we are writing the expression for loop 2, that is the reason why I2 minus I1. Clear? I2 minus I1. Clear? Now instead of this particular the resistance we are directly placing the value of R2. Okay, now see, the most important step is only this one only. When we are writing the loop 1 we need to concentrate only on this particular R2, and when we are writing for the loop 2 also we need to concentrate only on this particular R2, because if you are going to place instead of positive sign if we are placing negative sign, or instead of negative sign if you are placing positive sign, then the solution will completely wrong. Okay, now here this one is clear. Okay, so VR2 is equal to I2 minus I1 into R2. Clear? So here the most important point when we are talking about the current flowing through R2 is, in loop number 1 current direction is downwards through R2, and current direction I2 current direction is upwards. It means what, we need to take the difference of that particular I1 and I2. That is the reason why what I am doing, the potential of I1 is always greater than I2, and when we are writing the expression for I2 in loop number 2, so always we are taking I2 minus I1, because we need to take the difference of that particular I1 and I2, and in this case I2 is greater than I1, that's why I am taking I2 minus I1 for loop 2 and I1 minus I2 for loop 1. Clear? Now we know the value of VR3 and VR2. Now substitute these two values in this particular expression, that is equal to V applied voltage is 0 is equal to VR3 is how much, VR3 is I2 into R3 plus VR2 is how much, I2 minus I1 into R2. Clear? Now 0 is equal to, so here I2 into R3 value how much, we know that R3 is 20 ohms, plus what is the value of I2, we don't know, because we need to find this value only. Next R2 is how much, 10 ohms. Now here 0 is equal to 20 I2 plus 10 I2 minus 10 I1. Clear? Now 20 I2 10 I2, it means, so take common I2 from this particular expression, you will get 20 plus 10 minus 10 into I1. Clear? So here now 0 is equal to I2 into 20 plus 10 means 30 minus 10 into I1. Now 0 is equal to 30 I2 minus 0 is equal to 30i2 minus 10i1. Now what we are doing, we are sending this particular minus 10i1 to the left side, then you will get what? So 10i1 is equal to 30i2. Now here from this, what I am doing, I am writing the expression of I1 in terms of I2. The expression of I1 in terms of I2 means how we are going to write? We are going to write this particular expression like this. So 10i1 is equal to 30i2. That means 10i1 is equal to 30i2. From this expression, I am writing the expression of I1 in terms of I2. That is 30 divided by 10 into I2. Now 0 0 cancel, then I1 is equal to 3I2. Clear? So this is the expression we need to consider as 2. Now what we need to do? We need to substitute this equation number 2 in equation number 1. Clear? So substitute equation 2 in equation 1. Now by substituting equation 2 in equation number 1, so what is the expression of equation 1? Actually the equation number 1 is this one. Okay, this one, that is what? 15i1 minus 10i2 minus 10 is equal to 0. That is what? So 15i1 minus 10i2 minus 10 is equal to 0. That is only na. 15i1 minus 10i2 minus 10 is equal to 0. Now substitute, instead of this particular i2, substitute this value. Clear? Now here, so 15 into i1 means how much? 3i2 minus 10i2 minus 10 is equal to 0. Now 15 3s are, it means what? How much? 45i2 minus 10i2. So minus 10 is equal to 0. Now here 45i2 minus 10 means you will get 35i2 minus 10 is equal to 0. Now here 35i2 is equal to 10, then I2 is equal to 10 divided by 35. So by simplifying this one, you will get, so 10 divided by 35 means you will get 0.2857. Okay, so you will get, so 0.2857 amperes. Clear? So this is the value of what? I2 is equal to 0.2857 ampere is the value of I2. Okay, now assume equation number 3, this one. Now I2 value 0.2857 is clear, but we don't know exactly the value of I1 because this equation number 2 is I1, but this is in terms of I2. That is the reason why what we need to do, substitute equation 3 in equation number 2. Okay, now equation number 3 in equation number 2 means, so I1 is equal to 3I2, then I1 is equal to 3 into, so 0.2857 ampere. Now I1 is equal to, so by multiplying this one 0.2857 into 3, then you will get the value of 0.8571 amperes. Clear? So now by using mesh analysis concept, so by using mesh analysis concept, we got the currents which are flowing in the loops. That is I1 is equal to 0.8571 amperes. The value of I2 is equal to 0.2857 amperes. Okay, so this is the solution we are going to getting for the given network by using the concept of mesh analysis. Clear? So this is a procedure we need to follow for any type of problem. Okay, so in the given problem, in this problem we have only two loops, that's why we are getting two expressions. By simplifying those two expressions, you are getting the currents which are flowing in the loops. For example, sometimes in the network, in some other networks, he will give you 3 4 5 like this. Then it means what? You need to apply KVL for you need to apply KVL in individual loops. You will get individual expression from individual loop, then simplify all, you will get the values of currents which are flowing in the loops. Clear? So thank you so much for watching, and please do subscribe my channel, and also please like, comment, and please share with your friends. Thank you.